All right. Good afternoon, everyone. For those still here and still awake. I'm Tiago. I come from Nexmo, and I'll be presenting about a tool that we've been building for our infrastructure. So the outline for this presentation, I'll be talking about what we're doing at Nexmo. I'll be only talking about it very briefly, since there's a colleague of mine here, Cesare, that's also going to be presenting about that later on Thursday. Then we'll move right into the motivation behind the tool, the concept. We'll also speak about a lossy versus lossless codecs, so an issue that one needs to be aware of when doing this type of analysis. And also, we'll then talk about both iterations that the implementation went through and things that we already know that will be need to improve in the very near future. So we've been working on a conversation service at Nexmo. It's basically a context-aware API that tries bringing all the communication siloed APIs like SMS, PSTN, IP messaging, and IP voice together. And the final objective is that customers can build their contextual communications on top of their applications. There's also what we call VAPI, the voice API that's built on top of CAPI. And that's an API that allows customers to initiate and control calls to and from the PSTN. And then at the lower level, we have an abstraction, the media bridge, on top of FreeSWITCH that's providing an HTTP RESTful interface on top of FreeSWITCH. So this is the very high level diagram of how everything fits together. At the lowest level, we have the media bridge and FreeSWITCH. So the media bridge talks with FreeSWITCH using sockets. So it writes the messages using sockets and receives events through the sockets. Those events are then passed to CAPI, which figures out what to do with those events. It can end up sending those events to a customer endpoint or even somewhere around on our internal stack. So from the previous slide, you can see how important FreeSWITCH is on our internal stack. It's actually very crucial because everything is built on top of it. So it gets important to us to be able to know when things are going wrong. And in this case, things can go wrong in several different ways. So it can be network topology changes. So it can be either us making changes on our network, like adding a new server or adding a new route or changing a route, or even changes on parts of the network that we're not in control of. So our providers may change things on their network, affect our customers, and we're not even aware of it. Then there's also the changes on the media server side. So in this case, FreeSWITCH. So we can make changes in the configurations, change codecs configurations, which ends up badly. We can even change the source code ourselves and screw up. And also because of the nature of the project, which is open source, and it's not always aligned with the vision of a specific company. And so although it's still bad, it's easier when these changes result in total failure, like compilation errors or calls failing. But it's a lot harder when those changes result in working deployments, but they get the performance halved. And that results in latencies that ultimately result in bad quality for our customers. And so the concept is pretty simple. It's building a tool that's able to make outbound, that's able to place outbound calls, to receive inbound calls, and then ejecting a signal on those outbound channels, waiting, receiving that signal back, and being able to match what was put on the outbound and what was received on the inbound, and measuring the latency between that. So this is where the PowerPoint would have been handy. So that first slide on the left, this is one issue that one needs to be aware of when doing this type of latencies, this type of analysis, which is lossy versus lossless codecs. And that first slide on the left, we have two signals. It's basically the original signal from a WAV file, and then the encoded PCMA signal. And the two signals, you can see basically that the two signals overlap, almost overlap each other. If we zoom in, you can actually see some differences on parts of the signal. But this is pretty much the nature of lossless codecs. So they guarantee a certain degree of compression, but in the end, they also guarantee that they're able to recover the original data. If we go to a lossy example, so in this case, the same signal coming from a WAV file and then encoded using Opus, you can clearly see that they don't even, they almost don't match. And if we zoom in, you can see in the left side of the graph, the zoomed in graph, that the blue signal, so the original one, is much more abrupt than the encoded one. And that's pretty much the nature of lossy codecs. They basically, what they do is they have perceptual modules that try to emulate our hearing, our human hearing model, so our brain plus our ears. And to achieve those high degrees of compression, they are able to discard things that they perceive as redundant and that our brain wouldn't be able to pick it up anyway. And so that's how they achieve those high rates of compression. And so having that in mind, we chose to integrate with FreeSWITCH versus building our own standalone tool. Pretty much because FreeSWITCH already provided the needed stack, so it already does and places the outbound calls, it receives the inbound calls, it deals with the signaling and setting up the RGB sessions. And its modular architecture makes it really easy to build new features on top of the already existing core functionality. It was also a fact that both of our operations and QA teams were already using it daily, so there was no need to bring another tool on the deck. And there was already some in-house knowledge about its internals and the way it works. This doesn't mean, obviously, that this can't be applied in a standalone tool, but these were the reasons that made us chose to integrate with FreeSWITCH. So here's the architecture of the module. We have for each call that's placed for performing the analysis, we have 3 threads that are set up and run. We have the outbound thread, the inbound thread, and the matching thread. The outbound thread is basically responsible for writing the signal, the data on the outbound channel. Then the inbound thread picks up whatever comes on the inbound channel. And the matching thread, it's the thread that executes the algorithm that matches the outbound with whatever was put on the outbound with whatever it's coming on the inbound. So more specifically, for the first iteration, the outbound thread would read data from a file, like a WAV file. It would compose the frame, and on this first iteration, we were using sequence, an incremental sequence number to mark the frame. And so it would compose the frame, it would mark the frame with that incremental sequence number. It would write the timestamp and write a duplicate of that frame on an outbound buffer, and then finally write that frame on the outbound channel. The inbound thread would read an inbound frame, and it would write the timestamp and then write that frame on an inbound buffer. And so the algorithm for this first iteration would, the matching thread would basically scan the inbound buffer looking for frames, and for each frame it would check the sequence number, and based on that sequence number it would try to find a match on the outbound buffer, and if there was a match it would measure the difference between the timestamps. However, there's a major drawback with this approach, and there is that in real world use cases, it won't work because some hops of the network might override some RTP headers like timestamps and sequence numbers. So for the second iteration of the implementation, we set out to implement the algorithm in getting rid of the sequence numbers. So our thinking was that we could basically the least information that we would put on top of the data, the least problems we would have in the future integrating with real world use cases. And so it was actually advised, our voice architect Neil advised that we could probably use an echo canceller algorithm in order to do the matching between what was being put on the outbound and what was being received on the inbound. And so the echo problem is actually a very old problem on the telephony world. Imagine that you're speaking with someone and you're hearing that person on your voice system through the speakers. The voice of that person bounces on the walls and gets injected through the microphone of your voice system. And so that person ends up hearing herself with a certain delay. And so that's the echo. And the way it's solved is by placing an echo canceller on that voice system. That echo canceller, that box in the middle, you can see it as kind of an array of values, so a set of values, what's called the weight filter tabs. And what they do is basically they try to create a model of an expected echo signal based on the original signal that then goes and cancels the actual echo that gets injected in the system. And so for our implementation, there are several algorithms for implementing an echo canceller. For our implementation, we chose to go with the most well-known one. It's the LMS, least mean square algorithm. Problem with that algorithm specifically is that most of the variants that exist for that algorithm are applied on the time domain, and they're applied on a sample by sample basis. And so in terms of computation, it gets really heavy. However, there's one variant of that algorithm, which is the fast block LMS, and that's applied on a block so frame by frame basis. So this whole flow runs only for each frame, and it also uses it's also processed on the frequency domain, which means that it takes advantage of the computation efficiency of the FFT transforms. And so what we do is we basically, on the second iteration, we basically take an outbound frame from the outbound buffer. We move it into the frequency domain, which then gets multiplied by those set of values that adapt according to the input value, to what's received on the inbound, which initially are 0. Then we get the expected signal. That expected signal then needs to be converted back to the time domain, so it gets subtracted with what we actually received on the inbound, and that generates an error, and that error is then used to calculate the new values for those weight filter taps. And so this goes on and on again and again until the error starts stabilizing. And only when the error gets pretty close to 0 is when we do our measurements. And that's when we have convergence. So the drawbacks for this algorithm is that compared to the first iteration is a bit less efficient because they're bound by the FFTs, which are analog then. And the other one was pretty much searching for or in a sequentially ordered array. So for the future work, we need to integrate this with more real-world cases, so you can improve the tool. There's also, I think, that we can improve the convergence that we're seeing on the tool, and we will also probably be introducing like quality measurements on the tool and providing like MOS and PESC results in the near future. Yeah, that's it. Questions? It's not open source yet. We're trying to move towards that, yes, but it's not open source yet, no.
Any other questions? In the white shirt, go ahead.
Sorry, can you repeat that?
I believe there are some RTP measurements being, statistics being kept in FreeSWITCH because I can see them in the XML CDR. So could you have used them to do the latency measurements versus writing your own module?
Yeah, we could probably use something like that. The point of building a tool like this is that we can put ourselves in the position of the customers and pinpoint like any node in the network and loop back the call, so we can actually analyze the signal and check the latency. And it also puts us in a better position for in the future having like performing quality measurements on that signal. So that was the point of building the tool.
In the black over there, go ahead.
Sorry, I can't hear you from here. I just heard that you're on the website. The projects that I've talked about here, yes. So
Website that aren't. Oh, just wondering about the other projects on your website. They look pretty interesting. Are they very similar in terms of using FreeSWITCH or similar kind of infrastructures?
yeah, so the projects I've talked here, the VAPI, CAPI, the Media Bridge, they all use FreeSWITCH underneath. But that's going to be more, my colleague will talk more about that on Thursday. So if you want to hear more about that, yeah.
Any other questions? All right, big round of applause.
Thank you.
Thank you.